Hello and welcome back. So right now we are on this topic of powder characterization. Which is about evaluating the powder particles for their different properties like size, shape and other characteristics. And in the previous class we talked about different kind of shapes and how they are defined, and then we were also talking about how to define the particle size, if you remember, where we had discussed this characteristics dimension that can be used to define the size of a particular particle. So now what happens when you actually do the particle size analysis? The problem is most of the powders will have complex shapes, okay, and therefore it is difficult to define one single geometric parameter which will give the size of the particle, right? And therefore what is done is, for most of the particle size analysis, a particular geometric parameter is used, and a spherical shape is assumed. And the basis for this particular geometric parameter can be one of those geometric characteristics or geometric values like the surface area, projected area, the maximum dimension, or minimum cross sectional area or volume. And this is explained here in this particular slide over here as to how to define that geometric parameter to come up with a single dimension parameter which can be used to define the size of the particle, right. So this is an example of a particle which is irregular in shape. So what we can do, we can define it in terms of an equivalent sphere which is having either same projected area, same surface area or same volume, okay. So if we assume that, like how I said in the beginning, then the size of the particle can be defined in terms of the diameter of a sphere which is either having a same projected area, same surface area or same volume as the particle which is being measured. Okay. So, when you talked about the equivalent spherical diameters, these are the three bases for that, and if you consider each of them separately, this is what you are going to get. This is for equivalent spherical diameter which is based upon the projected area. So, here what is done is the area of the particle is equated with the area of an equivalent sphere. So, in this case the diameter is based upon the area. So, it is written as dA. So, that is the projected area of the sphere which is set equal to the area of the particle, and from here you get the projected equivalent diameter dA as square root of 4a by pi, okay, like what you see over here. Similarly, when you set the surface area of the particle equal to the surface area of the equivalent sphere, then you have so in this case this is the surface equivalent diameter written as ds, and therefore ds is given as square root of s by pi, that you can see over here also. Similarly, the volume equivalent diameter dV, if you consider that, and hence dV is given as this, given as this. Okay. So, that is how considering this as a sphere, the size of any particle can be defined in terms of one of these diameter, either dA, ds or dV. Okay. And as I said before, these are the different geometric parameters or geometric dimensions which can be considered as a parameter, as a geometric parameter to define the dimensions of the particle, like the projected height h, which is over here, the projected width w, or the maximum dimension. For example, in this case the maximum dimension is the maximum chord length m, right. So, this is how first you need to define the characteristic dimension, and then using the available instruments the particle size is measured. Okay. Now, the particle size can be measured by different techniques using different instruments, and each of these techniques uses a particular basis for measurements, and therefore, it is always good to mention what is the basis what was used for measuring the particle size when the particle size data is presented. Okay. So, talking about the particle shape now, like how we have defined the particle size in terms of an equivalent sphere having either similar projected area, similar surface area, or similar volume. The particle shape, especially for the irregular particles, can also be defined in a similar manner, wherein we use what is called a shape index, and a geometric parameter, again for example the specific surface area S can be used as the shape index. And for spherical particles, specific surface area per unit mass can be used as the shape factor. And if you see it for the spherical particle from this, where this is the surface area and this is the mass, where rho is the density, then the shape factor becomes 6 by rho d. Okay. Now, for irregular shaped particle, since there are more than one dimensions that has to be considered, many a times this aspect ratio is taken as a parameter to define the shape, and it is nothing, the aspect ratio is nothing but the ratio between the smallest and the largest dimension of the particle. And there again you can consider the equivalent diameter to define that ratio, like what is being shown for this particular particle over here, wherein d0 or d0 is the diameter of the outer embracing circle, as you could see over here, and dA is the diameter of the circle with equal projected area, which is this one. Okay. So, if you take the ratio of these two, this can be used as the aspect ratio for a particle like this. Okay. Now, if you talk about the measurement techniques for the particle size, there are different approaches and different instruments are available, and as I would have said before, each of these techniques or the instruments which are used uses a particular basis for measuring the particle size. Okay. Microscopy, where you actually see the particles under a microscope, is a population based technique, because here you can capture the image of the particles and then calculate or see the number of particles in a given area or so on. And therefore, it is a direct method to obtain both particle size and particle shape, because as I said here, you actually see how the particles are, and using certain analysis you can easily derive the particle size from the images which are captured on a microscope. Okay. And what kind of microscope will be used, that will depend on the size of the particles. If you have larger particles which are bigger than 1 micrometer, then optical microscope can be used, right. But we all know that the optical microscopes have their own limitations in terms of the highest magnification that can be achieved, and therefore, when the particle size is smaller, then we will have to go for electron microscopy techniques, for example, the scanning electron microscope or ACM. Okay. And the other advantage that you have in the ACM technique is that it will also show the surface topography, and it also permits composition and analysis of the particles. Okay. And the particle size can be easily obtained by the image analyzer, which many times come with the microscope itself, and this kind of technique is not suitable to measure particle size distribution, right. So, there are two things when you talk about particle size. One is the size itself, and another is how the size distribution is. That means how the powder is in terms of a different mix of sizes, right. Because it is generally, most of the time it will be generally a mix of different size of particles in a powder, and therefore, it is also important to know what are those different sizes present in a powder, and that is what is known as the size distribution, right. In order to get this distribution, it is recommended that other techniques are used, because microscopy, as I said, is not really suitable for measuring the particle size distribution. But here the advantage is you actually see the particles directly, and you can physically measure their size and get to know the actual size of the particles. And the other method or the other basis, as I said, is the weight basis, and this is one such technique which is one of the oldest method, that's the sieving process, wherein you use a series of sieves having a different mesh size, like what you can see over here. Okay. So, each of these sieves you can see having a different size of mesh. Starting from here to here, if you go in this direction, the mesh size is decreasing. So, what is done is in this case it is basically passing the powder successively over a series of sieving screens having progressively smaller openings. Okay. So, this is how they are arranged, this is how the instrument looks like, and if you see the arrangement of these screens, it is in this direction, it is increasing in this direction. So, when the mesh size increases, that means the particle size is decreasing in this direction. Okay. right. So that means the topmost screen that you have, that is having the largest opening, and the bottom one that you have is having the smallest opening. And mesh is defined in this way. Mesh is nothing but the number of wires per inch, and therefore if you say 200 mesh, it is actually 200 wires per inch. And if you convert the mesh size to the actual size in terms of the micrometer, there are standard charts available where you can see for each mesh size what is the corresponding size in terms of the micrometer. For example, for 200 mesh it is 75 microns, right. Similarly, for other mesh sizes you can get the corresponding size in micrometers. And this kind of plus minus designation is used to define the particle size in this case. For example, if you say minus 100 plus 200 mesh powder, that means that this kind of powder particles will pass through a 100 size mesh, but not through 200 size mesh, right. So the particle size is between 100 and 200 mesh size. And as I said, this is a weight based technique. So the powder is first loaded on the topmost screen that you have over here, and then this whole thing, this whole setup is closed, and then it is given a shaking motion, right. This is the motion direction. So this will be shaked, and as you shake it, these particles depending on their size will pass through these different screens, and after a certain time, once you stop it, the particles retained on each of the sieve will be collected, and their weight will be measured, right. So that is how, for each size, how much weight is retained on each of these screens will be measured, and that is why this whole technique is weight based. So when you see a particle, a particular size of particle being retained on a particular sieve, the size would be between the mesh size of that screen on which it is retained and the one above it, okay. So that is how this plus minus sign or the plus minus designation comes into picture to define the size between these two screens, okay. One which is having the powder and the other which is just above it, okay. So before we finish today's class, let us take a summary. We talked about the basis for particle size measurement, and we have seen that a particular geometric parameter can be chosen to define the size of a particular particle. If it is a regular shaped particle like a spherical particle, it is easy to define that geometric parameter. For example, the diameter of the sphere can be simply taken as the size of spherical particles. But for other kind of particles, you have to take a particular basis to define the size. And these are the different geometric parameters which can be considered to define the size of the particles. And when you make an assumption of a spherical particle, then the equivalent diameter of the particle of the equivalent diameter of the sphere is used as the particle size, and the basis for that equivalent sphere could be a similar projected area, similar surface area, or similar volume as the particles which is being measured. Okay. And these are the three different equivalent diameters based upon either the projected area, surface area, or volume. Okay. Similarly, we talked about the particle shape and how it can be again defined based upon the equivalent diameter, like what we have seen for the particle size. So, here for irregular shaped particles, generally a ratio between the linear dimensions of the particle is taken. The ratio is called the aspect ratio, and that can be also calculated based upon the equivalent diameters, like what you can see in this case for this particular particle which is irregular. And then we had seen that there are different bases of particle size determination. For example, if you are using a microscopy technique, it is population based, where you actually see the particles in a microscopy and you can see their actual size and morphology, and calculate the number of particles having a particular size and so on. And the other one is weight based, where you actually calculate the weight which is remained on a particular screen which is being used to separate the particles in terms of their sizes. Okay. So, these are the things that we have learned today in terms of the shape and size of powder particles, and with that we come to the end of this class. Thank you for your attention.